In the last session, we talked about find S algorithm. That find S algorithm actually outputs the maximally specific hypothesis. So it has considered only the positive examples and it ignores the negative examples, and the output of the find S algorithm is the maximally specific hypothesis. But there are certain issues with find S algorithm. The first one is we are getting an answer that is we are calling as maximally specific hypothesis. Whether we got it the correct target concept, whether we arrived at correct target concept, that is the first question. We are not very sure about that. Secondly, we are always starting with most specific hypothesis, including all pies. So that hypothesis where we included all pies, that was our starting point. Now the question is why we should start with the most specific hypothesis. What is the necessity? So that is another problem with our find S algorithm. Then number 3, though we have training examples, they may not be consistent, they may not be error free, they may not be noise free. So if they have some noise, that may lead to the wrong hypothesis. And the fourth limitation is there may be in many situations there may be more than one maximally specific hypothesis. In that case, there should be a backtracking facility to accommodate other hypotheses, but that backtracking facility, backtracking feature is not present in find S algorithm. So in order to overcome the limitations, we have another algorithm called candidate elimination algorithm. This algorithm depends on the definition of version space, which is indicated by Vs H comma D, where H is the set of hypothesis, D is the set of training examples, and which is actually it is a set of consistent hypothesis. There may be many hypotheses which may be consistent only with one example or two examples, but here our definition is a set of consistent hypothesis consistent with all, or a set of hypothesis, let us put this in this way, hypothesis which are consistent with all the data or training examples. That means for each H hypothesis, for each hypothesis H and training example D, h of x, maybe D is a set x, h of x should be equal to the target concept given in the training examples. In that case, we say that h is consistent with x. That means not only with x, what is version space? Set of hypotheses which are consistent with all the examples, x, y, z, so on, all the examples. So in candidate elimination algorithm, we are going to find it outputs version space. That means we will have a set consistent hypothesis. So this is the background of candidate elimination algorithm. Now let us go to the algorithm with the same example. Now we will start with on one hand there are 6 attributes. So here we are defining a boundary called most specific hypothesis, which we call as S naught, which there are 6 attributes. So 6 pi values, pi comma so 6 times pi 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 pi, totally 6 pi's. Let us make this size bigger. This is on boundary. This is S naught. We say this as specific boundary. On one other hand, we will have general boundary. Do you remember what is the most general hypothesis? Most general hypothesis contains, it will accept any value. Most general. That means most specific hypothesis means it will not accept any values. That means on any given day he will not enjoy the sport. Most general hypothesis G naught means on given any day, any situation, he will enjoy the sport. So we will accept any value in the hypothesis. So this is most general boundary which will accept any value. That means on any given day he will enjoy the sport. Whereas most specific boundary, he will not enjoy the sport at all, whatever may be the situation. So in between, what we try to do is, we try to examine each data training example, and based on that, what we are going to do is, with each example, with each training example, we try to generalize the most specific hypothesis. We try to make it more general to fit the training example, and we will try to make G naught, most general hypothesis, as more specific to fit the training example. This is what we are going to do. That means with each example we are going to modify this, especially whenever it is a positive example we will try to modify the specific boundary, and whenever it is negative example we will try to modify the most general. And after modifying, so to be specific with each positive training example we will generalize the most specific hypothesis. Then with each negative training example we will try to make G naught or general hypothesis more specific, and this is one. And the second task we are going to do with the negative example is we are going to remove the hypothesis which are not consistent with previous positive training examples. We will see this one in this example. So let us start. Let us take the first example. What is the first example? It is a positive example. So what we have to do, we have to accommodate, we have to modify so this is your first example. So we have to modify our S naught accordingly. Now S naught is saying that it will not accept any value, but as per the first training example we are sure that it will accept sunny in the weather, the cloud, the sky, and warm, the air temperature, and normal, and strong. So what we are doing, we are trying to modify the most specific boundary in order to fit the positive example 1. So this is our S1. What we have done, we started with most specific and we tried to adjust it, modify the S naught with the first training example. That is the first training example. Now take the second. So what about the most specific boundary, most general boundary? Our general boundary is already satisfying it is accepting any value, so it is consistent with the first boundary, first hypothesis, first training example. So it is G1 is equal to G naught. There is no change in the general boundary because it is consistent with the either sunny or any value, either warm or any value. So it is, there is no need to update. Now take the second example. What is the second example? Sunny, warm, high, strong, same. That is also another positive example. Sunny, warm, high, strong, warm, same. Now compare S1 and the second training example. So now we will prepare S2. So what about S2? S1 says sunny and training example says sunny, so no modification. It is warm and they are also warm, no need of any modification. Here training example is saying if the humidity is high, he will enjoy. My hypothesis is saying from the previous example, if the humidity is normal, he will enjoy. Both are true. Whether humidity is high or whether humidity is normal, in both the situations he will enjoy. So, to accommodate both the values, normal as well as high, I will replace that with question mark. So, here by question mark what I am saying, either normal or high, and then strong, here strong, no need of change, warm and warm, there is no change, same and same. So, this is your S2. What about G2? Because this is a positive example, it already satisfies the general boundary. So, G2 is equal to G1 is equal to G0. Now, the third example, this is a negative example. When it is negative example, we have to modify the general boundary. Now, what it is saying, if the sky is raining, he will not enjoy. That means when he will enjoy, what is the opposite of rainy here in the data? Sunny. So, I am writing hypothesis that if it is sunny, he will enjoy, because he is saying we have this negative example. Let me change the color, it is a negative example. So, he is saying if the sky is rainy, he will not enjoy. But my training example, because my training example is saying that, what I am concluding that if it is sunny, he will enjoy. He is saying if it is cold, air temperature is cold, he will not enjoy. So, what is the other option for me? If it is warm, he will enjoy. So, I am writing an hypothesis, warm. Why warm? Because if it is cold, he will enjoy. He will not enjoy. Then high. What is this high? Humidity. So, he is saying if the humidity is high, he will not enjoy. So, what is the other option for me? Normal. If it is normal, he will enjoy. So, let me write another hypothesis, normal. Next, strong, he will not enjoy. So, then when he will enjoy, the alternative to strong is not present. So, I cannot write a hypothesis. So, I am skipping that. Then warm. Warm, he will not enjoy because it is a negative example. Opposite of warm is cool. So, I will write here cool. Then change, he will not enjoy. Then same, he will enjoy. Because in change it is negative, I am taking the positive opposite, and same. So, these are the set of hypotheses which we can call as G3. But wait, we have to test them with the previous examples. What are the previous examples? 1 and 2. Now, let me check with 1. If it is sunny, he will enjoy. So, my G3 is also saying sunny, no problem. Warm, he will enjoy. First example is saying warm, he will enjoy. Then, this saying if it is normal, he will enjoy. First example is saying normal, he will enjoy. Then, if it is cool, he will enjoy. But my first example is saying if it is warm, he will enjoy. That means this hypothesis is not consistent with example 1. So, what I am doing is I am striking it off, I am removing from G3. What about same? The first example is same, forecast is same. So, our G3 is refined as, now we will remove this after comparison with first training example. Now, what about second example? Now let us compare with the second example. Here it is sunny, sunny, no problem. Warm, warm, no problem. Here, if the wind is or humidity is high, he will enjoy. But here it is normal, he will enjoy. That means it is contradicting the second positive example. This is generated from negative, but it is contradicting the second example. So let me remove this one also. So our G3, what about same? Same, same. So it is also removed from G3. So we got only 3. Now what is the next example? Fourth example. It is again a positive example. With every positive example, we will be modifying the. What about S3? Because it is positive example, S3 is same as S2. Sorry, if it is negative example, so we didn't modify anything with specific boundary. Now it is positive. So let us form S4 now. Let us update and form S4. Sunny, sunny, warm, warm, question mark and high, no problem. Strong and strong, okay. But here warm and here it is cool. Both are correct because both are from positive example. So to accommodate that one, I will make question mark. Then change and same. I want to accommodate both because they are positive examples, question mark. Now let us test G3 with example 3. Example 3. Sunny, no problem. Warm, no problem. But it is saying same, but here it is saying change. So this has to be removed when we compare it with the fourth example. So now the G4, so this is the answer. The set of the version space we got is the set of 3 hypotheses. So from these we can form some more hypothesis. We can form in between. Now because this is sunny, and I can keep warm and I can make all the question mark. That is another more general than this, more specific than this. Then another I can form sunny, keep all the question marks, and strong. That is one. Then we can keep all these things question marks and warm. So this is the version space where we have 1, 2, 3, 4, 5, 6 hypotheses as a set. Actual answer is S4 and G4. In between we can indicate it with an arrow mark. Actually because this is more specific. And So this is more specific symbol. So this is the most general and this is the most specific. We got totally 3 hypotheses. From that we generated in between, from that so totally we got 6 hypotheses. This is candidate elimination algorithm.